am excited to introduce Olin Downey to Google. He's a prolific author. He's a professor and an amazing guy. Olin worked here at Google from 2009 to 2010, and I see some people out in the audience who probably remember him from that time. He helped us analyze network performance, and we've been in touch ever since. Since then, he's been teaching, designing curriculum, and writing. He's also been using statistics and large data sets to answer interesting questions, dispel myths, and teach us how to properly analyze data. I always look forward to talking with Olin and reading his blog posts. And I finished his recent book in just over the weekend. I mean, I couldn't put it down. It was so good. And then, in fact, my son saw it on the bookshelf, and he picked it up, and he also read it in just a couple days. This latest book, Probably Overthinking It, Olin discusses many fascinating topics. And in particular, I spent 10 years working on Google Flights, and in the book, he's got just a couple paragraphs where he talks about how to passengers on flights, they always seem like they're full. But the airlines don't always see it that way. They think a lot of their flights are empty. And he's just got a great discussion of that, as well as so many other what seem to be paradoxes. So without further ado, Olin, I hand the floor to you.
Great. Thank you very much. I really appreciate that introduction. So I was on the faculty at Olin for almost 20 years. I left just a couple of years ago. And I've been working on a series of books that are about programming and data science and physical modeling. And the one that I've been working on most recently is Probably Overthinking It. So I have to say that Google bears some of the blame for this project. I was here in 2009 and 2010. One of the things that I worked on was a statistics library that eventually evolved into empirical dist, which is a Python package I use for several of my books, including this one. And while I was here, I participated in a relay race with a Google team up in New Hampshire. One of the things that I observed was length-biased sampling, this observer effect when you are in the race and you see people at different speeds. And I started a blog. This was, I think, the second article that I wrote in 2011. And that blog eventually turned into this book. So that example, the relay race example, is from chapter 2. This book started out as just a collection of blog articles. That's what I thought it was going to be. But one of the things that I found is that in every chapter, there was at least one example that wasn't just a toy problem. It was something that had real impact in the world. And that became the centerpiece of that chapter. So today, I'm going to talk about chapter 7, which is called Causation, Collision, and Confusion. And the confusion part is serious. It has consequences for lives. So I'm going to start with the low birth weight paradox, which is one of the first examples. This comes from a paper in 1971. It was a researcher in California who was looking at the relationship between mothers who smoke and the health outcomes for their children. And a few of their results, one of them was that the babies of mothers who smoke tend to be lighter by about 6%, and they are more likely to be classified as low birth weight, meaning that they fall below a particular threshold. And that was no surprise at the time. That was known to be true. They also found that if a baby is classified as low birth weight, it has higher mortality by quite a lot. So the background rate was about 8 per 1,000 at the time. This was in the 70s. It's better now. But for low birth weight babies, it was substantially higher, about 170 per 1,000. And again, that effect was known. But the thing that was surprising is that if you are researching low birth weight babies, so you select just those babies, what you find is that the babies of non-smokers are actually healthier. Sorry, I said that the other way around. The babies of smokers are actually healthier than the babies of non-smokers by almost a factor of 2. The mortality rate is about 50% lower, again, for babies of mothers who smoked. So that was surprising. And he wrote about it. He said, this raises doubt against the proposition that cigarette smoking acts as an exogenous factor. In other words, that it is harmful to babies. So in other words, he thought that maybe maternal smoking is not bad after all. And the media picked that up. There was a newspaper report that said, mothers needn't worry, smoking little risk to the baby. Or an article in Family Health magazine of all places that said they were in defense of smoking moms. And there was a retrospective paper in 2014 that looked back at the impact of this research and said that it probably held up anti-smoking measures for about a decade. So that had consequences for lives. Another example is the obesity paradox. This is a little bit more recent, from 1999. And this is a paper that looked at the relationship between obesity, kidney disease, and mortality. And they found a similar pattern, which is that obesity is one possible cause of kidney disease. Kidney disease does, in fact, increase mortality. And obese people in general have higher mortality. So again, none of that was surprising. But the thing that was surprising, if you select people who are being treated for kidney disease, it turns out that the ones who are obese were living longer. And this was called the obesity paradox. What they speculated was that, well, maybe overweight patients have more adipose tissue, and they are less likely to suffer from energy deficits. Maybe. This led to decades of confusion, which you can see just in the titles of papers. Between 2006 and 2019, we have the obesity paradox, fact or fiction. Still a controversy. Perception versus knowledge. Is this real? Yes, the paradox exists. Where do we stand? I'll tell you in a minute where we stand, but one more example. Again, more recently in 2000, a twin paradox, and this is not the one pertaining to relativity and the speed of light. This is the relationship between the mortality of multiple births, like twins, and depending on gestational age, which is how many weeks of pregnancy they were born. So again, three results that were familiar. Multiple births are more likely to be preterm. Preterm births have higher mortality. And multiple births do indeed have higher mortality. But again, if you select only preterm births, if that's your topic of research, you find that multiple births, twins, triplets, have lower mortality than others. And again, they had a possible mechanism, a possible explanation for this, which is that twins are in better health prior to 36 weeks of gestation. But then they do not enjoy the benefit of the additional time as much as single births do. Okay, maybe. Or maybe all of these paradoxes are committing the same statistical error. I'll explain that these are all examples of what's called informally Berkson's paradox. But really not a paradox. It is a form of sampling bias, and it's a particular form called collision bias, and I'll explain why. So I'm going to start with a simple example, and then we're going to work our way back up to those examples from epidemiology. If you took the SAT or the ACT or other standardized tests, you might remember that there are two sections, verbal and math. And you might wonder how they are correlated, so let me ask you all if you'll vote. If we look at math scores and verbal scores, do you think that they are correlated, anti-correlated, or unrelated? So correlated, anti-correlated, in the general population. I should say, of people who take the tests. Okay, so a lot of votes for correlated. And in fact, if we go get some data, this is from the National Longitudinal Surveys of Youth. They have test scores for about 1,000 people. And this is the verbal score on the x-axis, the math on the y. And visually, you can see that they look pretty strongly correlated. And in fact, the correlation is about 0.7. So that's quite strong. If you meet someone whose verbal score is 600, that's about 100 above average, you would expect their math score to be about 570, which is about 70 above average. So fairly strong correlation. All right, so that's the answer to question number one. Among everybody who takes the test, they're strongly correlated. But now suppose you go to a university and you sample a student population. On that campus, do you think it's correlated, anti, or not? Correlated? Anti-correlated? Not correlated. Okay, good guesses. They're all correct. It depends on the selection criteria. So I want to start with a hypothetical elite university where you have to get a total. The sum of your two scores has to be 1320 or better. I picked that because it means that both scores are 700 on average. So those are high scores, highly selective college. What that means is that if we go back to this scatter plot, everybody in the lower left in orange does not get admitted to elite university. Only the people in the upper right do. And in blue, if we plot a regression line through those points, we see that it has a negative slope. And in fact, the correlation is about negative 0.3. So at elite university, if you meet someone who is a little bit above average in their verbal score, above the local average, I mean, you would expect them to be a little bit below the local average in math. So in the general population, these scores are highly correlated. In this sample, they are anti-correlated. And depending on what the selection criteria are, we can make that correlation almost anything we want. So here's how that varies. On the x-axis, this is the minimum total score that you need to be admitted. And the y-axis is the correlation that you get in the selected sample. So over on the right, at 1320, that's elite university that we were just looking at, and that's -3. All the way on the left, at a college, hypothetically, that takes a random sample from the general population, you see the natural correlation at about 0.7, and you can get anything in between. And in fact, it can be even stronger than that. So if you go to what I'll call Secontier College, and let's say that you need a total score of 1200 to get in, but if you get 1300, maybe you get admitted somewhere else. And so now we see a scatter plot where people on the left were not admitted. People in the upper right went to a different school. And so the ones who enroll at Secontier are the blue ones. And again, if we put a regression line through that part, we get a correlation of negative 0.8. So we've induced a very strong anti-correlation because of this selection process. Once you are aware of Berkson's paradox, you will start to see it everywhere. This is an example from Jordan Ellenberg, where he pointed out that in the population of men, if you date men or prospective partners, there's the great square on two axes, from ugly to handsome and from mean to nice. And inside that is the triangle of acceptable men in the upper right-hand corner. And he pointed out that among the handsomest acceptable people, you'll see the full range from mean to nice. But someone who is relatively ugly in this population would necessarily be nice. They would be in that upper left-hand corner. So even if there's no correlation in the general population, the selection process here would induce this negative correlation. Hannah Fry presented another example of this in this YouTube channel, Numberphile, where she suggests that a film adapted from a novel is never as good as the book. And she offers this explanation. This is the great square of books and films. On two axes, the goodness of the book and the goodness of the movie. And the conjecture is that if something is in the lower left-hand corner, if it's a bad movie made from a bad book, you probably never hear about it. You will only hear about it if it's one or the other. So you'll be in that upper right-hand corner, and you'll see again that negative correlation. So either it's so bad it never gets into a film, or it's so bad that you've never heard of it. And again, Even if there's no correlation in general, we've induced a correlation because of the selection process. Now, you might be seeing a pattern here, which is that in these two-dimensional examples, we're selecting often one corner of the possibilities, and that corner has a correlation that's different from the general population. So we're always in this upper right-hand corner. And this is a more general idea of what causes this, which is that there are two ways to get into the sample. So there are two ways to be admitted to elite university. You have to be really good at one or the other or both. There are two ways to get into that small triangle of acceptable partners, and two ways for a book or a movie to get your attention. And that two ways is the key to those examples that I gave from epidemiology. So to remind you, the low birth weight paradox, again, babies of smokers are more likely to be low birth weight. Low birth weight is bad, it has higher mortality, and babies of smokers do in fact have higher mortality. But then the weird part is that if you select low birth weight babies, the babies of smokers have lower mortality. The reason is there are two ways that a baby might be low birth weight. One possible cause is maternal smoking, but then there are a whole bunch of other things, including birth defects, that might account for it. And if it's not one, it's more likely to be the other. And of the two, maternal smoking is less harmful. It's not good, but it's less bad than birth defects and other possible causes. So one way to think about this is what I call Berkson's toaster. So imagine the scenario, you smell smoke coming from the kitchen, and you get to the kitchen and you discover that there's burnt toast in the toaster. You would probably feel relieved. Because of all the things that could cause smoke in your kitchen, burnt toast is probably the least bad. And I think it's the same scenario. Imagine you're a doctor, you're treating a patient who is low birth weight, and you find out that the mother is a smoker. You might be relieved because that explains it, and it provides a relatively benign explanation that's better than the alternatives. So the heroes of this story are Hernandez-Diaz, Schusterman, and Hernan, who published this paper in 2006 that explains the low birth weight paradox. They used data from the National Center for Health Statistics. They had 3 million babies from 1991. And so they replicated Yerushalmi's study from 1971. Looking at the distribution of birth weights, we can see the blue line there. Those are babies of smokers. They are in fact lighter on average and more likely to fall below that threshold and be classified as low birth weight. And if we look at mortality here as a function of birth weight, you can see the crossover point that is Berkson's paradox. So above, let's say, 2,000 grams at birth, the mortality rate is higher for children of smokers, which is what we expect. But below that threshold, we see that reversal, where the mortality rates are consistently lower for babies of smokers. What this paper in 2006 did was to explain why that was happening using a causal diagram, a causal network that links these factors: maternal smoking, birth weight, infant mortality. And they actually drew several possible causal diagrams for this scenario. I'm going to pick one that is relatively simple and sufficient to explain what's going on. So in this diagram, an arrow means that A causes B. So the arrow here from smoking to mortality means that smoking is a cause of mortality. It is also a cause of low birth weight. And then there are other unknown risk factors which potentially also cause low birth weight and also cause mortality. So this diagram is a graphical representation of those hypotheses. If we think that those causal factors exist, this diagram shows that. And to be clear, what I mean by cause here is, first of all, statistical. Doesn't mean it always happens, but it increases the probability of that outcome. And not just a correlation, but causal in the sense of a counterfactual, like if that had not happened, the outcome would not have happened. And here we can see that two ways to get in effect, which is that there are two causes of low birth weight. And so again, if we know that one of the causes exists, the probability of that other cause goes down. The other thing that we can see in this diagram is that those two arrows coming into one effect, that is called a collider, just because visually those arrows are colliding with each other. And so this sampling process, if we select based on low birth weight status, this is an example of collider bias. That is a possible explanation of the low birth weight paradox. The obesity paradox lived a little bit longer. This is from 2017, explaining why it might not be a paradox after all. And the diagram is very similar. Here we have obesity that causes heart failure. Heart failure causes mortality. But there are other risk factors that potentially cause both of those things. And again, there are two causes of heart failure, which means that if you know that it's one, the other is less likely. In this case, I think it's less certain that collider bias is a complete explanation. It is still possible that there's an actual mechanism going on. It's possible that obesity has an actual benefit, as they speculated, but also that it might be informational, that if a patient being treated for kidney disease is overweight, that might reflect the fact that they are relatively healthy or a relatively recent diagnosis. The twin paradox was explained in 2000, and maybe embarrassingly, it was explained in the same issue of the same journal where it was published. So there was a companion article that said, "Are appearances deceiving?" And they may well be. Again, the diagram is very similar. Of all the things that could cause preterm birth, multiple birth is probably the most benign. Everything else is probably worse. So I mentioned causal diagrams because they are a powerful tool for understanding situations like this. I hope you had the same experience I did, which is feeling confused about this and then seeing the diagram and then almost feeling silly because it's almost obvious. So I should say, each of these diagrams represents a possible explanation, but there are multiple versions of it, and they are any of them sufficient to explain the problem. So in this example, if I have another arrow, if it turns out that obesity also contributes to mortality, or if there are other conditions that might be caused by obesity, we can add those to the diagram. They help with the explanation. It's also useful to augment the diagrams with magnitudes. So here I'm using shading and heavier arrows to suggest stronger effects. And in fact, to get Berkson's paradox, to get the reversal of the sign of the effect, you do need conditions on what these strengths, what the strength of these causal relationships are. And finally, the causal diagrams give us a vocabulary for talking about these things. So I mentioned a collider. If you have two arrows coming into a single effect, that's an example of a collider. If you have a mechanism where an effect, A causes B, and then B causes C, that thing in the middle, that other condition here, is a mediator. And if the arrow goes the other way, if you have some other condition that causes both obesity and mortality, that would be a confounder. And this now gives you rules, or at least guidance, for how to work with data sets like this. If you use a collider to select your sample, as we did with the SAT scores and as people did with low birth weight, or if you add a collider as a control variable in a regression model, you are going to induce a biased view of what those relationships are. And I should say, biased in this case does not mean, oh, it might be off by a little bit. As we saw in this example, it can be off by a lot. So if the right answer in the general population is 0.7, and you estimate that it is negative 0.8, you are about as wrong as you could be. I mean, you're correct in describing the sample, but wrong in making an inference about the population. We are not yet out of the woods. This is an article from last year that talks about several recent studies. One of them, among diabetics, eating ice cream was associated with lower risk of heart problems. That sounds great. And for overweight people, a dairy-based dessert was associated with reduced insulin resistance. So I have not looked closely into these. I have not looked at the data. I can't quite dismiss them out of hand. But when I see things like among diabetics, it sounds very much like you have selected for a collider. And among overweight people, I would guess that collider bias explains those counterintuitive results. Now, if you don't happen to be an epidemiologist, you might wonder whether you need to worry about this in the data that you look at. You might. Anytime you read a research paper, and especially if it got public attention, well, there are two ways for new research to get attention. It can either be novel or good. So the more novel it is, the less likely it is to be correct. And similarly, the things that we read in the media are selected by negativity bias in the media. If a story is negative, it's more likely to get published. And negativity bias in our heads, which we are more likely to pay attention. And so this, if you think about it, when you see negative stories reported, they are somewhat less likely to be true. Last, if you're studying any kind of customer sample, you should think about how does someone get to be your customer? And there are at least two ways, but one possibility is that they like your product. The other possibility is that they didn't have a choice. And I would speculate that as market share increases, there are probably more and more of that second group. And so you might see customer satisfaction going down and very likely inducing lots of other correlations among various properties of your customers, again, because of this sampling process. So last I'll mention, again, you start to see this everywhere. I saw this tweet about a year ago about a burrito place that looks dingy, the food is greasy, it comes in styrofoam, and their website is a 404. And I was really happy to ruin this joke by explaining it. I said, this is an example of Berkson's paradox. You should read about it in my book, where I explained, again, there are two ways that a restaurant might be successful. Either it's a nice place or it has good food, and if it's not one, it's more likely to be the other. I'm not the only person who thinks about these things. Tyler Cowen pointed out that there are two ways that a dish can appear on the menu. And one possibility is that it sounds good, and so people order it. But the other possibility is that it is surprisingly good, and so it's still on the menu. And so he recommends ordering the least appetizing thing on the menu. So to sum it all up, this is my perfect advice for a perfect date. Find someone unattractive because they'll be nice. Take them to a restaurant in a strip mall. Order something that sounds bad. Go to a movie that's based on a bad book. So take that advice and report back. As I mentioned, this is chapter 7 of Probably Overthinking It. There are 11 more chapters that are just as fascinating as this one. So I hope you get a chance to read it. I hope you enjoy it. If you want to see works in progress, you can follow my blog at Probably Overthinking It. And we have some time to take some questions.
Thank you, Alan. That was really great, really fascinating, as fascinating as all the book. We have an open mic here, so I invite people to come up and ask questions. Come on up.
Hi, Dan Margo. So in the SAT example, the anti-correlation was induced by the geometry of the selection function. And I'm wondering, are there selection functions that would have a geometry that would not bias the underlying sample? Like if I was trying to come up with an admission criteria for an elite university that didn't bias the population, what would you suggest?
Right, good question. So you're right, we looked at a couple of geometries. There's everything in the upper right-hand corner. There was sequentier, where it was kind of a slice through the middle. There's the either-or criteria, where you have to exceed a threshold on one or the other, but maybe not both. So I looked at a few geometries. Those examples all induce a negative correlation. It's a good question. I mean, artificially, you could cut a slice out, in any way that you wanted. But I can't think of a natural process that would happen in the real world that would not make it negative. I can't think of a good example.
It seems like if you have a sufficiently wide range, you get the same correlation as the underlying sample, even if it doesn't include the entire underlying sample. Like, it doesn't need to be a scatter plot of the underlying sample, it just has to be a broad enough slice that the slope is correctly captured.
Right, right. Well, so here's an example. Let's say that you want a well-rounded student body, and so you want people whose scores have a maximum distance between them.
Yeah.
And if someone is too imbalanced, you don't want them. So that would select a stripe right through the middle of the diagram, and it would be highly correlated.
Okay. It
Cool.
works.
I hadn't thought of that, but thank you.
Thanks.
That will go in the sequel.
Hi, my name is Bhargav. Thanks for the great talk. Thanks for the book. I haven't read it yet. But one thing that struck when I was hearing your talk was, I remembered a book I read sometime back, which spoke about confirmation bias. And you start off with a hypothesis, you collect all the data to prove what you want to show. So for example, you start with the claim that, there's a strong correlation between verbal and math skills, and then you hunt for that data, and then you say, yeah, see, I proved it. So there is some confirmation bias at play. So does your book talk about that, number one? Number two, probably a dumb question, I should read the book, but why is it called Probably Overthinking when the example was clearly showing that it was underthinking? We are not really looking at all the samples. Thank you.
Good question. Well, the title comes from the blog, and the blog is kind of me making fun of myself. And the example that I mentioned at the beginning of running a relay race, I'll tell you that example in order to explain what I mean when I say probably overthinking it. So in a relay race, it's not the case that everybody starts at the same time. There's a staggered start, and different people come onto the course at different times. So when you start running, you see something that looks more like a sample of the general population in the race. But when I started running, what I found is that when I overtook somebody, I blew right past them. And then there were some really fast runners who just overtook me and I never saw them again. And I started thinking in my oxygen-deprived state that maybe the people who run these races, lots of fast people like to run them, and lots of slow people like to run them. But people in the middle like me, for some reason, this is not the format that they enjoy. And I realized after a bit that I had been fooled by length-biased sampling, where in that case, my probability of seeing someone when I was on the course was proportional to the difference between their speed and mine. So if they were super fast, I would see them. If they were super slow, I would see them. But if somebody else was out there running at exactly my speed, and I didn't happen to see them when I first joined, they and I would be going along and we would never see each other. And you can figure out what that sampling process looks like and in fact run it backwards in order to infer what that notch looks like that you missed. So that's the kind of thing that I think about when I'm running, and that's why it's called Probably Overthinking It. The other part of your question was about, it sounded like partly sampling, but also partly cherry-picking data as a way of getting a confirmation bias. You find what you look for because you select the data sets that support it. And yes, that can certainly happen. In this particular example, the National Survey of Youth, they're pretty good about getting a representative sample, so they've done a lot of the work for me. Not everybody takes SATs and ACTs, so in a sense, that's already a subset of the population. You can think about what effect that has. Those are my thoughts.
Thank you.
Thank you.
Hi, I'm Margaret Lee. Thanks for the talk. It's really interesting. I'll definitely read the book. So you introduced like a few terms in your talk, like this collision bias, this Berkson paradox, and people are talking about confirmation bias. And I like all these terms, but a lot of times with these terms, I worry that like we're going to start labeling them on everything, and we're going to be making these same statistical errors where we're confusing things as one paradox when it's really another thing. So what do you recommend as a statistician, when you look at data, do you try to put them into these categories of these terms you learn, or is your idea when you're trying to understand confusing things to write out causal diagrams, or do you have another approach? Like, how useful are these terms for you, or do you find they also confuse things more often?
Right, yeah. I think the terms are useful, but they have their limits. And so, in fact, some of the examples that I gave, like a restaurant, the probability that it survives depends on whether it's good food or a good location. So that's partly Berkson's paradox, but it's also a version of survivorship bias, which is I'm less likely to see a restaurant. Yes, yet another term. So I don't think they're necessarily useful because you have to put every peg into the right hole, but they give you a vocabulary for talking about it and a checklist as you are working with a data set. What are the things that I should worry about? And certainly the sampling process. How did I get this data is something that you should always think about, because many of these biases, by the time you've selected the data, it's too late. There's nothing you can do to undo that bias other than go back and try to get a better sample. So I do think they're useful terms for both vocabulary and as a checklist, things to think about. Make sure you're not fooling yourself.
Yeah, the checklist makes a lot of sense. Thanks.
Thank you.
Hi there. It seems this idea that, well, there's this sort of exogenous other that feeds into everything. Seems like nice for explaining uncertainty, but it seems like it can make almost anything a collider if it's an intermediate node, right? There's that exogenous other factor that's feeding into every single node on your graph. How do you sort of can you talk a little bit about how you quantify that and figure out what's a real collider and what's really, oh yes, other is always a cause?
Yes, good question. So you say you could take one of these causal diagrams and you could add a lot more factors and you could add a lot more lines. And in fact, one of the papers that I mentioned, they had 6 or 7 different versions. So when do you stop? And that's where I think causal diagrams are a little bit limited if you draw the same arrow for every cause and effect. But when you start adding weights to them, I think that's the key thing, which is it's a model. And a model means that you have to decide what to include and what to leave out. And so if you have reason to think that a cause is relatively weak, that's a candidate to leave it out. If you leave out something that is actually a really strong effect, that's where things go wrong. So I think that would be my answer is, yes, potentially if you add enough arrows, everything's a collider, everything's a confounder. But if you start thinking about what are the strong effects that I really need to take into account, you can start pruning that diagram and get it down to something that's useful in practice. One of the ways, and I see someone coming up and I'll take that question in just a second, but one of the ways that I think it's most useful is thinking about what kind of analysis you should do with the data. So if you look at the diagram in one hand, that will give you a lot of guidance about what you potentially add as controls or as explanatory factors in a regression model, like a confounder. Controlling for a confounder is a great idea. Controlling for a collider is a terrible idea. And what these diagrams let you see visually is which is it? And I think you're less likely to mess up.
Hey, it was a little surprising to me when the idea that even if you control for the collider, you still end up in the same place. And I think thinking about some of your scatter plots, I think I've talked myself into why that would be the case. I was curious if you've seen examples in the wild where they do, it's not just selection, they have the full square, but because of that control, they've come up with something that turns out to be misleading.
Right. Yes. And I have to say, you made me nervous when you said that it was surprising, because that's often a very subtle way of saying that I've made a mistake. So, but thank you. No, that's a good question. I don't have good examples off the top of my head of like a research paper where they ran a regression model and they included a collider and therefore the result was wrong. There are examples, and I should start to find some. But that, I think, is the practice in a lot of fields, is the idea that more controls is always better.
Right.
And
that's kind of my intuition, is whenever I see a paper with a surprising result, one of my first questions is, what didn't they control for? Because that seems to be usually my first way I can skewer it. And so for the answer to be, you controlled for too many things, that was genuinely intuitively surprising to me.
Yes, yes. There's one example that's called the Everest paradox, which is an example of controlling for a mediator, which is to say that if you control for altitude, the atmosphere at the top of Mount Everest is 70 degrees and comfortable. And the problem is that there's a mediator. The altitude causes the cold temperature. And so if you control for control for altitude, you have controlled away exactly the thing that's causing the effect.
Thank you.
Hi, thank you for coming. I really was really expecting a really interesting talk. I got a really interesting talk, and I got a really interesting book, which I was not expecting. It's actually not the first book I've gotten from you, and I was wondering if you were inspired by the examples here, and maybe had some brainwaves that went off, you thought about something, and you wanted to explore in simulation or using statistics of your other books, how would you recommend using those books, or starting with one of those books to get at some more, to generate your own examples and analyzing them?
Thank you.
Thanks.
I appreciate the question. I will mention that each book in this chapter, I actually wrote the book in a Jupyter notebook and then translated it into other formats. And I've released the Jupyter notebooks. So if you want to explore any of the examples in the book, you can go to the repository and check out a notebook. They all run in Colab. So you don't have to install anything. You can press a button and run the entire chapter. If you are starting into data science, I do have a sequence that I can recommend, which is if you want to learn Python, the 3rd edition of Think Python is coming out next month. That is also available in Jupyter notebooks. And from there, both Think Stats is probably the best preparation for this book. And then Think Bayes is the alternative. There's not a lot of explicit Bayesian statistics in this book, with the possible exception of the base rate fallacy. But if you're interested in Bayesian statistics, Think Bayes is a way to get started. So thank you.
So Alan, I have a question. I mean, you kind of mentioned here that you see Berkson paradox everywhere you look. How many of those are you going to write up? I mean, do you have a whole queue of questions you'd like to address, and what might some of those future ones be?
I do. So I keep notes, and I have a bunch of notes for a possible sequel. Maybe Definitely Overthinking It, working title. And I hope that as people read the book, that light bulbs will go on, and they'll send me more suggestions. I got that with the inspection paradox, which I mentioned, the relay race. I've had several people who popped up and suggested other versions of that. One of them is, why is the customer service department always experiencing greater than normal loads? And yes, that's probably nonsense, but it could almost be true, because you are inducing that load. And the fact that you're calling at that particular time suggests that it is probably a busy time. I can mention one other example of this, which is driving back from the eclipse in Vermont. I was in a traffic jam that the app insisted was going to end in 30 minutes, and then it was clear sailing. But by the time I got there, it was no longer clear sailing because everybody else arrived at the same time as me. So we were this bolus of traffic that was both causing and experiencing the traffic jam. This is the basis of, you are not in a traffic jam, you are a traffic jam.
And since I'm here, I got another question. I often look at data and I say, oh, I really should slice this way or that way. Am I just inviting Berkson's paradox?
Good question. And breaking a data set up into groups and looking at groups is, of course, a useful thing. The question is partly what you're trying to accomplish. If you're trying to make an inference about the general population, and you take a slice out of the population that's not a representative sample, that is potentially hazardous. But you can also make the opposite mistake, which is if you have a large group that is made up of disparate subgroups, sometimes you need to break it up because the relationship in the subgroups might be an entirely different shape from the relationship when you put all of those groups together. And that's the basis of Simpson's paradox, which is chapter 11.
Excellent. And for me, one more. I go to the doctor a lot, or not a lot. I go to the doctor like most people would go to the doctor.
The average amount.
I get advice from the doctor. I sometimes wonder, is this advice true? And your book right here told me several examples where it took decades to sort things out. And especially if you were reading the popular press. I also have a mother who constantly sends me health articles. What should I do?
Yeah, and I guess there are two forms of bias there, which is, again, if something makes it into the media, it has been selected often because it's novel or counterintuitive, and often that means that it's wrong.
Delete button?
Yeah, but we're trying to get the right amount of skepticism, because one of the things that I don't want, if you come away from this book and you just think, oh, all statistics are lies, there are 100 ways to go wrong, every study that's ever been published is wrong, I think that's going too far in the other direction. Science really does create knowledge. We really can use data to answer questions and make better decisions. That is the real theme of this book. Now, on the one hand, you do need to be careful because there are easy mistakes to make, but I don't want to go to the opposite extreme of rejecting everything. We do make progress. Our knowledge at any point in time is imperfect. It's hard to know what's going to change, but we do have good reasons, justified reasons, to believe things that we believe. One of the chapters, for example, is about whether vaccines prevent illness and death. And my conclusion is that vaccines prevent illness and death. So that seems like worthwhile knowledge. And conversely, denying that is potentially hazardous.
Hazardous to your health, sure. All right, thank you, Alan. This was really fascinating. Really glad you came back to Google to talk to us.
Thank you all.